On behalf of the School of Arts and Sciences and Penn Engineering, I am very pleased to welcome you to the 6th annual Thomas and Yvonne Williams Lecture for the Advancement of Logic and Philosophy. We are most grateful for the generosity and vision that Tom and Yvonne have shown in establishing the fund that supports this series of lectures and that makes possible other educational activities at the university and at upper schools in our region. It was a great pleasure to work with Tom when I first arrived at Penn and to watch him develop through the study of logic and philosophy that clarity of mind which he has so successfully brought to bear in the sphere of practical affairs, and that sustains his ongoing passion for the life of the mind. And it remains a great pleasure to work with him now on a range of activities that will advance a general appreciation of the power of reason to clarify problems, both practical and theoretical. I am delighted to introduce this year's Williams lecturer, Penelope Maddy. Dr. Maddy is one of the leading philosophers of mathematics in the world. In 2002, she was awarded the Lakatos Prize for her book, Naturalism in Mathematics, which presents an illuminating investigation of the justification of the axioms of set theory. Dr. Maddy, a UCI Distinguished Professor of Logic and Philosophy of Science and of Mathematics, is a member of the American Academy of Arts and Sciences and is past president of the Association for Symbolic Logic. Please join me in welcoming Penelope Maddy, who will speak to us about objectivity in mathematics.
Thank you, Scott. I also want to thank Tom Williams and his wife Yvonne for making this lecture series possible. It's always a good thing, it seems to me, when you get the mathematicians and the philosophers into the same room, and it's not always easy to do that, so we're grateful. Thank you also, Scott and Michael, for the hospitality of the philosophy department. Okay. So one of the many things that makes the practice of mathematics, that makes the philosophy of mathematics so difficult, in fact, maybe the leader in that troublesome company, arises from the pure phenomenology of the practice, of what it feels like to do mathematics. Anything from solving a homework problem to proving a new theorem involves the immediate recognition that this is not an undertaking in which anything goes, in which we may freely follow our personal or collective whims. It is rather an objective undertaking par excellence. Part of the explanation for this objectivity lies in the inexorable quality of the various logical connections, but that can't be the whole story. If we try to treat mathematics simply as a matter of what follows from what, we capture the claim that the piano axioms logically imply 2 + 2 = 4, that some set theoretic axioms imply the fundamental theorem of calculus, but we miss 2 + 2 = 4 and the fundamental theorem themselves. Another way of putting this is to say that we don't form our mathematical concepts or adopt our fundamental mathematical assumptions willy-nilly, that these practices are highly constrained. But by what? One perennially popular answer is what constrains our practices here, what makes our choices right or wrong, is a world of abstracta that we're out to describe. This idea is nicely expressed by the set theorist Yanis Moskavakis. He says, "The main point in favor of the realistic approach to mathematics is the instinctive certainty of everybody who's ever tried to solve a problem that he is thinking about real objects, whether they are sets, numbers, or whatever," close quote. Often enough, this sentiment is accompanied by a loose analogy between mathematics and natural science. This is Moskavakis again. "We can reason about sets much as physicists reason about elementary particles or astronomers reason about stars," close quote. In keeping with our close observation of the experience itself, it seems only right to admit that mathematics is, if anything, more tightly constrained than the physical sciences. We tend to think that mathematics doesn't just happen to be true, it has to be true. Now, it's well known that so-called Platonistic positions of this sort are beset by a range of familiar philosophical problems. For myself, I'm more troubled by purely methodological concerns, but I won't go into those here, as I want to focus instead on one prominent line of reaction to these difficulties. This springs from a sentiment famously expressed by Kreisel, or perhaps I should say apparently expressed, as no clear published source is known to me. Dummett's paraphrase goes like this. He says, "What is important is not the existence of mathematical objects, but the objectivity of mathematical statements," close quote. Hilary Putnam casts this idea in terms of realism. He says, "The question of realism, as Kreisel long ago put it, is the question of the objectivity of mathematics and not the question of the existence of mathematical objects," close quote. Stuart Shapiro makes this connection explicit. He says, "There are two different realistic themes. The first is that mathematical objects exist independently of mathematicians, their minds and languages and so on. Call this realism and ontology. The second theme is that mathematical statements have objective truth values independent of the minds, languages, conventions, and so forth of mathematicians. Call this realism and truth value. The traditional battles in the philosophy of mathematics focused on ontology. Kreisel is often credited with shifting attention toward realism and truth value, proposing that the interesting and important questions are not over mathematical objects, but over the objectivity of mathematical discourse," close quote. So on this approach, our mathematical activities are constrained not by an objective reality of mathematical objects, but by the objective truth or falsity of mathematical claims, which traces in turn to something other than abstract ontology, say to modality, to mention just one prominent example. I bring this up because my hope today is to float an idea that would do Kreisel one better, an account of mathematical objectivity that doesn't depend on the existence of objects or on the truth of mathematical claims. To get at this in a reasonable compass, I'll have to skate over many themes that demand more detailed treatment, but I hope what amounts to an aerial overview of a book-length argument might be of interest nonetheless. The goal, then, is to uncover the source of the perceived objective constraints on the pursuit of pure mathematics. The test case here will be my longtime hobby horse, the justification of set theoretic axioms. What makes this axiom candidate, rather than that, into a proper fundamental assumption of our theory? The plan is to approach this question from a broadly naturalistic point of view, so let me quickly sketch in the variety of naturalism I have in mind. I apologize to those of you who heard this story yesterday. Imagine a simple inquirer who sets out to discover what the world is like, the range of what there is, and its various properties and behaviors. She begins with her ordinary perceptual beliefs, gradually develops more sophisticated methods of observation and experimentation, of theory construction and testing, and so on. She's idealized to the extent that she's equally at home in all the various empirical investigations, from physics, chemistry, and astronomy to botany, psychology, and anthropology. Along the way, this inquirer comes to use mathematics in her investigations. She begins with a narrowly applied view of the subject, but gradually comes to recognize that the calculus, higher analysis, and much of contemporary pure mathematics are also invaluable for getting at the behaviors she studies and for formulating her explanatory theories. Here she recapitulates the mathematical developments from the 17th to the 21st centuries. This gives her good reason to pursue mathematics herself as part of her investigations of the world, but she also recognizes that it is developed using methods that appear quite different from the sort of observation, experimentation, and theory formation that guide the rest of her research. This raises questions of two general types. First, as part of her continual evaluation and assessment of her methods of investigation, she will want an account of the methods of pure mathematics. She will want to know how best to carry out this particular type of inquiry. Second, as part of her general study of human practices, she will want an account of what pure mathematics is. What sort of activity is it? What is the nature of its subject matter? How and why does it intertwine so remarkably with her empirical investigations? In this humdrum way, by entirely natural stages, our inquirer has come to ask questions typically classified as philosophical. Philosophy undertaken in isolation from science and common sense is often called first philosophy, so I call this second philosopher. So, given that the second philosopher will want to pursue set theory along with her other inquiries, the most immediate problem will be the methodological one. How am I to proceed? So it makes sense to begin here. To get a feel for the forces at work, let's review some concrete examples, just to get some things on the table. In the early 1870s, Cantor was engaged in a straightforward project in analysis, generalizing a theorem on representing functions by trigonometric series. Having shown that such a representation is unique if the series converges at every point in the domain, Cantor began to investigate the possibility of allowing for exceptional points, where the series fails to converge to the value of the represented function. It turns out that uniqueness is preserved despite finitely many such exceptional points, or even infinitely many exceptional points as long as these are arranged around a single limit point. But Cantor realized that it extends even further. To get at this extension, he moved beyond the set of exceptional points and its limit points to what he called the derived set. He says, it is a well-determined relation between any point in a line and a given set P to be either a limit point of it or no such point. And therefore, with the point set P, the set of its limit points is conceptually codetermined. This I will denote P prime and call the first derived point set of P, close quote. Now, once this new set, the first derived set, P prime, is in place, the same operation can be applied again. With P prime, the set of its limit points is conceptually codetermined. This P double prime is the second derived set of the original P, and so on. Cantor then proved that if the nth derived set of the set of exceptional points is empty for some natural number n, then the representation is unique. Now, of course, there had been talk of point sets before Cantor navigated this line of thought, but here, for the first time, a point set is regarded as an entity in its own right, susceptible to the operation of taking its derived set. From a methodological point of view, what's happened is that a new type of entity, a set, has been introduced as an effective means toward an explicit and concrete mathematical goal, extending our understanding of trigonometric representations. Well, around the same time, Dedekind also made several early uses of what we now recognize as sets. The first came in algebra in his theory of ideals, where he elected, quote, this is Dedekind talking, to replace the ideal number of Kummer, which is never defined in its own right, but only as a divisor of actual numbers, by a noun for something which actually exists, close quote. This something which actually exists, the ideal number, Dedekind identifies with the set of numbers that Kummer would have taken it to divide. By sidestepping the computational algorithms that are central to Kummer's treatment, Dedekind was able to demonstrate that the theory could be developed non-constructively and to explain why the properties of ideal numbers didn't depend on the details of how they were represented. Here again, sets are being introduced in the service of explicit mathematical desiderata, representation-free definitions, abstract or non-constructive reasoning, though Dedekind's vision is broader than the above-cited example from Cantor. He introduces a promising new style of reasoning whose mathematical fruitfulness was dramatically demonstrated as abstract algebra went on to thrive in the hands of Noether and her successors. The same drive toward new numbers as actual objects with representation-free characterizations is on display in Dedekind's theory of the real numbers. Here, Dedekind's goal is to provide a perfectly rigorous foundation for the principles of infinitesimal calculus, and in particular to remove the, quote, geometric evidence that can make no claim to being scientific, close quote. Since the calculus deals with continuous quantities, he reasons that it should be founded on, quote, an explanation of this continuity. And he sets out, quote, to secure a real definition of the essence of continuity, close quote. The result, of course, is his elegant definition of continuity and construction of the real numbers. Competing theories of Weierstrass and Cantor begin from particular convergent series or sequences of rationals, identifying many equivalent such items to a single real. In contrast, Dedekind appeals to a cut, simply an infinite set of rationals. This approach wipes out all the detailed series or sequence structure, yielding one cut for each real, and the abstract characterization allows for broad generalization. So here again, we see Dedekind preferring definitions that aren't tied to particular representations, like series or sequences, while pursuing broader mathematical goals, a general theory of continuity, and of course the foundations of the calculus. Another important goal, also clearly present in his work on real numbers, is the pursuit of rigor. Dedekind says, in science, nothing capable of proof ought to be believed without proof, close quote. This declaration opens his account of the natural numbers, a third venue for his appeal to sets. Here he officially lays out his background set theory and goes on to develop his account of the natural numbers. In all these cases, we find Dedekind introducing sets in the service of explicit mathematical goals, a representation-free non-constructive abstract algebra, a rigorous characterization of continuity to serve as a foundation for analysis and a more general study of continuous structures, a rigorous characterization of the natural numbers and resulting foundation for arithmetic. Okay, now turning from the introduction of sets to the adoption of axioms about them, we find Zermelo in 1908 with a range of motives. Locally, he hopes to quiet the controversy over his proof of the well-ordering theorem from the axiom of choice. But more globally, he sees himself as contributing to, quote, the logical foundations of all arithmetic and analysis, close quote. He despairs of finding a compelling and fruitful definition of set on which to base the subject, something comparable, say, to Dedekind's definition of continuity and its role in founding analysis. And he opts instead to analyze the practice of set theory and, quote, seek out the principles required for establishing the foundations of this mathematical discipline, close quote. Of particular interest for our purposes are his reflections on the proper methods of justifying axioms. Presumably their foundational success counts in favor of his axioms as a whole, but when pressed on the axiom of choice in particular, Zermelo distinguishes evidence of two kinds. The first is intuitive self-evidence, which we might now describe as being implicit in the informal concept of set. Zermelo argues that choice must enjoy this sort of subjective obviousness on the grounds that so many set theorists have used it, often without noticing. But as we've seen, he despairs of defining the set concept with a precision adequate to development of the theory. Instead, he appeals to a second standard of evidence that can be objectively decided, namely, quote, whether the principle is necessary for science. And of course, he means mathematical science in addition to regular science. Here he lists various outstanding problems that can be resolved on the assumption of choice and concludes, quote, so long as the relatively simple problems mentioned here remain inaccessible without choice, and so long as, on the other hand, the principle of choice cannot be definitely refuted, no one has the right to prevent the representatives of productive science from continuing to use this hypothesis, as one may call it for all I care, and developing its consequences to the greatest extent. Principles must be judged from the point of view of science, and not science from the point of view of principles fixed once and for all. Close quote. This mode of defense goes beyond the observation that his axioms allow the derivation of set theory as it currently exists and the foundational benefits thereof. Zermelo here counts the mathematical fruitfulness of his axioms, their effectiveness and promise, as points in their favor. Gödel also recognized the importance of such evidence, for example, in this well-known passage. He says, even disregarding the intrinsic necessity of some new axiom, even in case it has no intrinsic necessity at all, a probable decision about its truth is possible also in another way, namely inductively by studying its success. Success here means fruitfulness in consequences, in particular in verifiable consequences, i.e. consequences demonstrable without the new axiom, whose proofs with the help of the new axiom, however, are considerably simpler and easier to discover and make it possible to contract into one proof many different proofs. There might exist axioms so abundant in their verifiable consequences, shedding so much light upon a whole field and yielding such powerful methods for solving problems, that no matter whether or not they are intrinsically necessary, they would have to be accepted at least in the same sense as any well-established physical theory, close quote. It has become customary to describe these two rough categories of justification as intrinsic, self-evident, intuitive, part of the concept, and such like, and extrinsic, effective, fruitful, productive. Okay, to round off this list of examples, we should consider a contemporary case. Determinacy hypotheses came in for serious study beginning in the 1960s as part of a broader search for new principles that might settle the problems in analysis and set theory left open by the now standard descendant of Zermelo's system, Zermelo-Frankel with choice, or ZFC. In his 1980 state-of-the-art compendium on the subject, Moskavakis observed that, quote, no one claims direct intuitions either for or against determinacy hypotheses. That, quote, those who have come to favor these hypotheses as plausible argue from their consequences, close quote. At that time, he concluded, quote, at the present state of knowledge, only few set theorists accept determinacy as highly plausible, and no one is quite ready to believe it beyond a reasonable doubt. And it is certainly possible that someone will simply refute it in ZFC. On the other hand, it is also possible that the web of implications involving determinacy hypotheses and relating them to large cardinals will grow steadily until it presents such a natural and compelling picture that more will succumb, close quote. Now here Moskavakis displays impressive foresight as more have succumbed in recent decades on the basis of new discoveries. In telegraphic summary, the current evidence for determinacy falls roughly into four classes. First, it generates a rich theory of projective sets of reals with many of the virtues identified in that passage from Gödel. Second, Moskavakis' web of implications relating determinacy to large cardinal hypotheses has indeed grown steadily. In the decade following Moskavakis' book, Martin, Steele, and Wooden, building on work of Foreman, Magador, and Shelah, showed that determinacy follows from the existence of large cardinals. and indeed it is now known to be equivalent to the existence of certain inner models with large cardinals. Third, a striking phenomenon in terms of consistency strength has emerged. In John Steele's words, quote, "Any natural theory of consistency strength, at least that of determinacy, actually implies determinacy," close quote. Given the long-standing foundational goal of set theory and the open-endedness of contemporary pure mathematics, we have good grounds to seek theories of ever higher consistency strength. If all reasonable theories past a certain point imply determinacy, this constitutes a strong argument in its favor. And fourth, in the presence of large cardinals, forcing cannot succeed in showing a question about projective sets to be independent. This means that if any question about projective sets is left unresolved by determinacy, this can't be shown by forcing. The independence involved would have to be a new and unfamiliar variety. Given that we want our theory of sets to be as decisive as possible within the limitations imposed by Gödel's theorems, this so-called generic completeness would appear a welcome feature of determinacy theory. So in short, the current case for determinacy has blossomed so impressively that many would agree with Hugh Wooden's assessment, quote, "Determinacy is the correct axiom for the projective sets." Okay. Assuming these examples are typical, the second philosopher hoping to undertake an investigation of sets has access to a rich array of methods, both for introducing sets in the first place and for determining their extent and their properties thereafter. In broad summary, these rest on the pursuit of various mathematical goals, from relatively local problem solving to providing foundations to more open-ended pursuit of promising mathematical avenues. Given what set theory is intended to do, relying on considerations of these sorts is a perfectly rational way to proceed. Embrace effective means toward desired mathematical ends. At the same time, she begins to appreciate the extent to which these methods differ from her familiar observation, theory formation, and testing. For example, she isn't accustomed to positing entities to increase her expressive power, as in Cantor, or rejecting a theory because it produces less interesting consequences, as with the alternative to determinacy's theory of the projective sets that results from Gödel's axiom of constructibility. She might reasonably wonder if her more familiar tried and true methods could be called upon to supplement or even correct these new approaches. On examination, though, she concludes that the answer here is no. Ordinary perceptual cognition is most likely involved in our grasp of elementary arithmetic, but she recognizes that this connection to the physical world has long since been idealized away in the infinitary structures of contemporary pure mathematics. Though Quine has argued that mathematical claims are empirically confirmed by a less direct route, this position appears to her to rest on accounts of science, mathematics, and the relations between them that don't accurately reflect the true features of these practices. Though she appreciates that providing tools for empirical science remains one of the central goals of pure mathematics, she also realizes that science no longer shapes the ontology or fundamental assumptions of mathematics as it once did in the days of Newton or Euler. Finally, cases like group theory, which was considered useless and nearly dropped from the curriculum at Princeton just years before it entered physics as an essential tool, such cases convince her that any effort to rein in the broad range of goals pursued by pure mathematicians would be unwise. So she's faced with an array of new justificatory methods that appear to be both rational and autonomous. Okay, now if all she ultimately cared about were answering questions of the first type, what are the proper set theoretic methods, she'd be done. But our second philosopher will also ask questions of the second type, beginning with a stark, are these methods reliable? Do they successfully track the existence of sets and their properties and relations? Of course, she's familiar with questions of this form. She investigates how ordinary perception gives her information about the medium-sized objects in the world around her. She examines the efficacy of our instrumental means of detecting the small parts of matter. She devises double blinds to reduce the risk of misleading experimental results, and so on. In all these familiar cases, she employs her usual methods to evaluate how humans, as described in biology, physiology, psychology, evolutionary theory, and so on, come to know the world, as described in physics, chemistry, geology, astronomy, and so on. The case of set theory is the same. She's observed the methods of set theorists and now wants to know whether or not they successfully track the truth about its subject matter. This raises a prior question. Should set theory be understood as describing a subject matter, as attempting to deliver truths about it? Now, as we've seen, the second philosopher differs from Quine in rejecting the idea that mathematics used in application is justified by ordinary empirical evidence along with the physical theory in which it's embedded. If she's to conclude that pure mathematics is a body of truths, her case for this will presumably rest more loosely on the way it's intertwined with empirical science. For now, I'd like to leave a bookmark at this point to return to it later. For now, let's assume that the second philosopher is justified in regarding set theory as a body of truths. And since she has no reason to take its existence claims at anything other than face value, she's also justified in believing that sets exist. Though she's viewing the practice from her external scientific perspective as a human activity, she sees no opening for the familiar tools of that perspective to provide supports, correctives, or supplements to the actual justificatory practices of set theory. She has no grounds to question the very procedures that do such a good job of delivering these truths, so she concludes that the proper methods to employ, the operative supports and correctives, are the ones that set theory itself provides. She concludes that the methods of set theory are reliable guides to the facts about sets. Okay, to this point then, the second philosopher has determined that set theoretic methods are rational, autonomous, and generally reliable. To explain why this is so, she must now delve more deeply into questions of the second type, about the nature of the human practice of set theory. She's now faced with the challenge of explaining what makes these methods reliable, what sets must be like in order for this to be so. Under the circumstances, the second philosopher is naturally inclined to entertain the simplest hypothesis that accounts for the data. Sets just are the sort of thing that set theory describes. This is all there is to them. For questions about sets, set theory is the only relevant authority. Various familiar conclusions fall out of this bare suggestion. Since set theory tells us nothing about sets being dependent on us as subjects, or enjoying location in space and time, or in participating in causal interactions, it follows that they're abstract in the usual ways. John Burgess sums up this particular sentiment nicely. He says, "One can justify classifying mathematical objects as having all the negative properties that philosophers describe in a misleadingly positive-sounding way when they say that they're abstract, acausal, non-spatiotemporal, and so on. But beyond this negative fact and the positive things asserted by set theory, I don't think there is anything more that can be or needs to be said about what sets are like," close quote. So let me call this thin realism. What's happened here is that the second philosophical thin realist begins from her conviction that the authority, her confidence in the authority of set theoretic methods when it comes to determining what's true and false about sets, and draws from this a metaphysical conclusion about the nature of sets, about their thinness. For this sort of realism, there's no troubling epistemological problem. Sets just are the kind of thing that we find out about in these ways. There's also no confounding worry about the determinacy of the continuum hypothesis. Set theory is describing the set theoretic universe V, and CH or not CH is a theorem. This is not a version of neo-Kantianism. Set theory doesn't tell us that sets are constituted by our practices or any such thing. Nor is it a version of Carnapianism. The decision about a new axiom isn't a merely pragmatic choice of a new linguistic framework. It's guided by reliable set theoretic methods, a new discovery about V. Now, despite these attractive features of thin realism, I think it would be disingenuous to ignore a nagging worry that it's all too easy, that rests on some sleight of hand. Connecting sets and set theoretic methods so intimately continues to invite the suspicion that sets aren't fully real, that there's a kind of shadow play thrown up by our way of doing things, by our mathematical decisions. The position would be considerably more compelling if it offered some explanation of why sets are this way, but any step in that direction, in the direction of an underlying account of sets that explains this fact, seems to lead us inevitably beyond what set theory tells us about sets. Now, in fact, I think something can be offered that draws the sting from this nagging doubt, but it won't take quite the form expected. What we want is a sense of what sets are that explains why these methods track them. What I think we can get from the thin realist's perspective is a sense of an objective reality underlying both the methods and the sets that illuminates the intimate connection between them. Perhaps this will be enough. Let me come at this question by asking what objective reality underlies and constrains set theoretic methods, what objective reality it is that set theoretic methods track. The simple answer, of course, is that they track the truth about sets. But our goal is to find out more about what sets are without going beyond what set theory tells us, and our hope is that asking the question this way might help. So, what constrains our methods? Part of the answer lies in the ground of classical logic, but our interest here is in the mathematical features. To get at these, let me draw a brief compare and contrast with Kant on geometry. So, according to Kant, the concept of a triangle is defined by us, so we can know what belongs to it. That is, we can know trivial analytic truths like all triangles are three-sided. In contrast, no amount of meditating on the concept of triangle will reveal to us that the three interior angles of a triangle are equal to two right angles. For this, we need to construct a triangle in our imagination or on the page, draw a line through the apex parallel to the base, and reason from there. How does this process take us beyond the concept to something synthetic? Kant's answer is that the constructions involved are shaped by the structure of our underlying spatial form of sensibility, either in pure intuition when we draw in our visual imagination, or in empirical intuition when we draw an actual diagram. Because of this shaping, the argument tracks more than just what's built into the concept. The derivation is also constrained by the nature of space itself, which, as we know, Kant thought to be Euclidean. Of course, this picture of geometric knowledge hasn't survived subsequent progress in logic, mathematics, and natural science, but I think it provides a helpful analogy with what I want to suggest in the case of set theory. Kant is out to explain what underlies the proof of this geometric theorem, what makes it a proof. His answer is not just the concept of triangle, not just logical consequence, but also the nature of the underlying space. We're out to explain what underlies the justificatory methods of set theory, what makes considerations of the sort we've sketched into good reasons to believe what we believe, what takes us beyond mere logical connections and allows us to track something more. And what is this something more? We're looking for the counterpart to Kant's intuitive space. Well, before trying to answer this question for set theory, let's first consider another type of case in which we go beyond the logical, namely in mathematical concept formation. In the logical neighborhood of any central mathematical concept, say the concept of group, there are innumerable alternatives and slight alterations that simply aren't comparable in their mathematical importance. Logic does nothing to differentiate these one from another, assuming they're all consistently defined. But group stands out from the crowd in getting at the important mathematical similarities between structures in widely different areas and allowing those similarities to be developed into a rich and fruitful theory. In ways that the historians of mathematics spell out in detail, group effectively opens the door to deep mathematics in ways the others don't. So what guides our concept formation, beyond the logical requirement of consistency, is the way some logically possible concepts track important mathematical strains that others miss. Now, of course, there are stark differences between group theory and set theory because the two pursuits have different goals. Group theory aims to draw together a wide variety of diverse structures that share mathematically important features. It'd be counterproductive to require that all groups be commutative, or not, because there are deep structural similarities between commutative and non-commutative groups that it's mathematically fruitful to trace. Set theory, on the other hand, aims at least in part to provide a single foundational arena for all classical mathematics. So it strives to develop a unified theory that's as decisive as possible, for example, that settles the continuum hypothesis. Still, there are overarching similarities. Set theoretic concepts are formed in response to set theoretic goals, just as the concept group is formed in response to algebraic goals. In large cardinal theory, for example, we can trace the conceptual progression from the super strong cardinal to the Sherlock cardinal to the wooden cardinal, which turned out to be the optimal notion for the purposes at hand. Or the gradual migration of the concept of measurable cardinal from its origins in measure theory to the mathematically rich context of elementary embeddings. Of course, the set theoretic cases we've been concerned with involve not definitions, but existence assumptions, like the introduction of sets in the first place or the addition of large cardinals, and new hypotheses, like determinacy. But in these cases, too, far more than consistency is at stake. These favored candidates differ from alternatives and near neighbors in that they track what we might call the topography of mathematical depth. This topography stands over and above the merely logical connections between statements, and furthermore, it's entirely objective. Just as it's not up to us which bits of pure mathematics best serve the needs of natural science, just as it's not up to us that it would be counterproductive to insist that all groups be commutative, it's also not up to us that appealing to sets and transfinite ordinals allows us to capture the facts about the uniqueness of trigonometric representations, that the axiom of choice takes an amazing range of different forms and plays a fundamental role in many different areas, that large cardinals arrange themselves into a hierarchy that serves as an effective measure of consistency strength, that determinism primacy as the root regularity property for projective sets and interrelates with large cardinals, and so on. These are the facts that play the role analogous to Kant's Euclidean space, the facts that constrain our set-theoretic methods. And these facts, unlike Kant's, are not traceable to ourselves as subjects. Now, a generous variety of expressions is typically used to pick out the phenomenon I'm after here: mathematical depth, mathematical fruitfulness, effectiveness, importance, mathematical productivity, and so on. I'm using such terms more or less interchangeably. But one point worth emphasizing is that the notion in question is not being offered up as a candidate for conceptual analysis or some such thing. To begin with, I doubt that an attempt to give a general account of what mathematical depth really is would be productive. It seems to me the phrase is best understood as a catch-all for the various kinds of special virtues that we clearly perceive in our illustrative examples of concept formation and axiom choice. That's why I rehearsed all that stuff for you earlier. But even if I'm wrong about this, even if something general can be said about what makes this or that bit of mathematics count as important or fruitful or whatever, I would resist the claim that this something general would provide a more fundamental justification for the mathematics in question. Our second philosophical analysis strongly suggests that the context-specific justifications we've been considering so far are sufficient on their own, that they neither need nor admit supplementation from other sources. It also bears repeating that judgments of mathematical depth are not subjective. I might be fond of a certain sort of mathematical theorem, but my idiosyncratic preference doesn't make some conceptual or axiomatic means toward that goal into a deep or fruitful effect of mathematics. For that matter, the entire mathematical community could be blind to the virtues of a certain methods or enamored of a merely fashionable pursuit, as we all know, without changing the underlying facts of which is and which isn't mathematically important. This is what anchors our various local mathematical goals. Cantor may have wished to expand his theory on the uniqueness of trigonometric representations, but if this theorem hadn't formed part of a larger enterprise of real mathematical importance, his one isolated result wouldn't have constituted such compelling evidence for the existence of sets. Similarly, the overwhelming case for Dedekind's innovations depends in large part on the subsequent success of abstract algebra that they helped produce. The key here is that the mathematical fruitfulness isn't defined as that which allows us to meet our goals, irrespective of what those might be. Rather, our mathematical goals are only proper insofar as satisfying them furthers our grasp of the underlying strains of mathematical fruitfulness. In other words, the goals are answerable to the facts of mathematical depth, not the other way around. Our interests will influence which areas of mathematics we find most attractive or compelling, just as our interests influence which parts of natural science we're most eager to pursue. But no amount of partiality or neglect from us can make a line of mathematics fruitful if it isn't, or fruitless if it is. Okay, thus we've answered our leading question. The objective something more that our set-theoretic methods track is these underlying contours of mathematical depth. Of course, the simple answer, they track sets, is also true. So what we've learned here is that what sets are, most fundamentally, is markers for these contours. What they are, most fundamentally, is maximally effective trackers of certain strains of mathematical fruitfulness. From this fact about what sets are, it follows that they can be learned about by set-theoretic methods, because set-theoretic methods, as we've seen, are all aimed at tracking particular instances of effective mathematics. The point isn't, for example, that there is a measurable cardinal really means the existence of measurable cardinals is mathematically fruitful in various ways. Rather, the fact of measurable cardinals being mathematically fruitful in various ways is evidence for their existence. Why? Because of what sets are, repositories of mathematical depth. They mark off a mathematically rich vein within the indiscriminate network of logical possibilities. So, I claim, there is a well-documented objective reality underlying thin realism, what I've been loosely calling the facts of mathematical depth. The fundamental nature of sets, and perhaps all mathematical objects, is to serve as devices for tapping into that well. This is simply what they are. And since set-theoretic methods themselves are tuned to detecting these same contours, they're perfectly suited to telling us about sets. This, I suggest, is the core insight of thin realism. Okay, so let me sum up the second philosopher's journey so far. She comes to realize that contemporary pure mathematics is a vital part of her investigation of the world and to regard it as a body of truths. She recognizes that its methods are new and distinctive, sees no opening for correction or defense from her more familiar methods, concludes in particular that theoretic methods are rational, autonomous, and reliable guides to the truth about sets. To account for this striking fact, she forms the simple hypothesis that sets are the sort of thing that can be investigated in these ways. And finally, she discovers the source of this fact, namely that sets simply are means for producing certain mathematically fruitful outcomes, and that set theoretic methods are expressly designed to track just these deep mathematical strains. Thus, thin realism presents itself as an attractive answer to our second group of questions. Set theoretic activity is the investigation of an abstract realm of sets. Its methods are reliable simply because of what those sets are. The whole enterprise answers to the objective topography of mathematical depth. The pursuit of new set theoretic axioms and of a solution to the continuum problem are legitimate parts of this inquiry. Okay, so we've achieved a kind of objectivity here, but despite its non-traditional aspects, it still relies on the existence of abstracta and the truth of our claims about them. What I'd like to do now is return to that point where we left the bookmark, the point where the second philosopher concluded that set theory is a body of truths, but her grounds were left vague. Eventually, I want to return to the question of what those grounds might be and to the extent to which they're persuasive. But let me first sketch in the position that results if we take the other fork in the road at that point. If we conclude that whatever its merits, pure mathematics just isn't in the business of uncovering truths. Well, if he's not uncovering truths, then what is the pure mathematician doing? In the case of set theory, we've got a sense of the answer. Among many other things, Cantor is extending our grasp of trigonometric representations, Dedekind is pushing toward abstract algebra, Zermelo is providing an explicit foundation for a mathematically important practice, contemporary set theorists are trying to solve the continuum problem. Just as the concept of group is tailored to the mathematical tasks set for it, the development of set theory is constrained by its own particular range of mathematical goals, both local and global. Mightn't the second philosopher rest content with this description? Set theory is the activity of developing a theory of sets that will effectively serve a concrete and ever-evolving range of mathematical purposes. Such a second philosopher would see no reason to think that sets exist or that set theoretic claims are true. Her well-developed methods of confirming existence and truth aren't even in play here. But she does regard set theory and pure mathematics with it as a spectacularly successful enterprise unlike any other. Let's call this position arealism. Now, we've noted that whatever reason the thin realist may have to count pure mathematics as true must rest somehow on the role of mathematics in empirical science. So we need to ask, can the arealist account for the application of mathematics without regarding it as true? There's a complex story to be told here, but examination of the historical and scientific record leads the second philosopher to believe that contemporary pure mathematics works in application by providing the empirical scientist with a wide range of abstract tools. The scientist uses these as models of a cannonball's path or the electromagnetic field or curved spacetime, which he takes to resemble the physical phenomena in some rough ways, to depart from it in others. Indeed, often enough in fundamental theories, we aren't sure exactly how the correspondence plays out in detail. The applied mathematician labors to understand the idealizations, simplifications, and approximations involved in these deployments of his abstract structures. He strives as best he can to show how and why a given model resembles the world closely enough for the particular purposes at hand. In all this, the scientist never asserts the existence of the abstract model. He simply holds that the world is like the model in some ways and not in others. For this, the model need only be well described, just as one might illuminate a given social situation by comparing it to an imaginary or mythological one, marking the similarities and dissimilarities. Assuming then that the truth or not of mathematics is irrelevant to explaining its role in scientific application, it appears that arealism is open to our second philosopher. She notes that mathematics is successful on its own terms and immensely useful to science, but since it isn't confirmed by her usual methods, even by her need to explain the role it plays in her empirical theorizing, she concludes that she has no grounds on which to regard its objects as real or its claims as truths. In philosophical taxonomy, the standard term for someone who doesn't believe in abstract objects is nominalist. If we limit attention to mathematical abstracta, the arealist would seem to qualify. But at least as nominalist is usually conceived in contemporary philosophy of mathematics, this way of talking seems to me to invite misunderstandings. Let me say a word about this. Recall that contemporary nominalism began with Goodman and Quine's enunciation of, quote, a philosophical intuition that cannot be justified by appeal to anything more ultimate, close quote. Namely, quote, we do not believe in abstract entities. We renounce them altogether, close quote. In Burgess and Rosen's characterization, quote, nominalism, as it is understood in contemporary philosophy of mathematics, arose toward mid-century. It arose among philosophers, and to this day is motivated largely by the difficulty of fitting orthodox mathematics into the general philosophical account of the nature of knowledge, close quote. To avoid nominalism, they say, one must, quote, explain in detail how anything we do and say on our side of the great wall separating the cosmos of concreta from the heaven of abstracta can provide us with knowledge of the other side, close quote. Now, various familiar ideas on the nature of knowledge in concrete cases, like the causal theory of knowledge and its successors, are then floated to highlight the severe obstacles that stand in the way of such an explanation. These elements provide the raw materials for a perfectly general, in-principle argument against abstracta of all kinds. Now, I hope and trust it's clear that this is not a portrait of our second philosophical a-realist. She doesn't come to her investigations with an a priori prejudice against abstract objects, or with any preconceptions about what knowledge must be like that would seem to rule out our knowledge of sets. She doesn't argue that set theoretic knowledge is problematic or impossible on principle. She simply surveys the evidence at hand and concludes that it doesn't confirm the existence of sets or the truth of our theory about them. So if a-realism is to be considered a version of nominalism, it certainly isn't what Burgess and Rosen call the stereotypical variety. All right. So now, at this point, we have two apparently second philosophical positions in play. Though they disagree sharply over truth and existence, the thin realist holding that sets exist and set theory is a body of truths, the a-realist denying both, still, they are indistinguishable at the level of method. On grounds like those that motivated Cantor and Dedekind, both would elect to introduce the sets into their pursuit of pure mathematics. Both would regard Zermelo's defenses of his axiom as persuasive. Both would follow the path of contemporary set theorists on determinacy and large cardinals. This methodological agreement reflects a deeper metaphysical bond. The objective facts that underlie these two positions are exactly the same, namely those distinctive strains of mathematical depth. For the thin realist, sets are the things that mark these contours. Set theoretic methods are designed to track them. For the a-realist, these same contours are what motivate and guide her elaboration of the theory of sets. She can go wrong as easily as the thin realist if she fails to detect the true mathematical virtues in play. For both positions, the development of set theory responds to an objective reality, and indeed to the very same objective reality. So what separates the a-realist from the thin realist, then, doesn't lie in their set theoretic practices or what underlies them. Where they differ is in their second philosophical reflections on the human undertaking called set theory. They would agree precisely on what counts as proper grounds for adding a new large cardinal axiom to the theory of sets. They would disagree only on the thin realist's added assertion that these grounds confirm the existence of the large cardinal in question and the truth of the corresponding axiom. Notice that this isn't an ordinary set theoretic claim of existence or truth that's at issue here. The a-realist, like the thin realist, will formulate the axiom in existential form and call it true in the sense of holding in V. Their disagreement takes place not within set theory, but in the judgments they form as they regard set theoretic language and practice from an empirical perspective and ask second philosophical versions of the traditional philosophical questions of the second group that we've been considering. So how is the second philosopher to adjudicate between thin realism and a-realism? This returns us at last to the problem that we've set aside twice. On what grounds does the thin realist judge that set theory is a body of truths? Given that she rejects the usual Aquinean arguments, given that she endorses the a-realist's account of how mathematics works in application, the second philosopher's case for thin realism will have to rest more loosely on the way mathematics is intertwined with empirical science. She recognizes that pure mathematics arose out of a subject very closely tied to our study of the physical world. She regards the project of providing a rich array of structures for the contemporary scientist as one of the overarching goals of mathematical practice. She well appreciates that contemporary pure mathematics continues to find its way into scientific applications, sometimes along deliberately anticipated paths and sometimes along wholly unanticipated ones. Thus, mathematics, whatever its idiosyncrasies, appears as an integral part of her overall enterprise, as opposed to astrology or theology or whatever, which are idiosyncratic without playing a part in that enterprise. On this picture, the second philosopher pursues mathematics in a spirit continuous with her other enterprises. Some of its methods, like logical deduction and means-end reasoning, are familiar. Others, like Cantor's, Dedekind's, Zermelo's, and the determinacy theorists, are unfamiliar, but taken to be rational and reliable along the lines that we've been following. Thus, the divergence between the second philosophical A-realist and the second philosophical thin realist comes down to this. As the second philosopher conducts her inquiry into the way the world is, beginning with her ordinary methods of perception and observation, theory, formation, and testing, she's eventually faced with the effectiveness of pure mathematics and elects to add it to her ever-growing list of investigations. She also recognizes that the appropriate methods are different and that the objects studied are different. The point at issue hinges on what she concludes from this. If the new objects seem a bit odd, non-spatiotemporal, acausal, and so on, but still enough like the old, singular bearers of properties, and so on. If the new methods seem a bit odd, but still of a piece with the old, then she concludes that she's made a surprising discovery, that the world includes abstracta as well as concreta. If, on the other hand, she regards the new methods and would-be objects as sharply discontinuous with what came before, she has no grounds for thinking pure mathematics is true, so she concludes that this new practice, valuable as it is, isn't in the business of developing a body of truths. So which is it? Is pure mathematics just another inquiry among many, or is it a different sort of thing that's immensely helpful to the others? Are the grounds cited by Cantor, Dedekind, Zermelo, and the determinacy theorists just more evidence of an unexpected sort, or are they the trademarks of a different sort of activity altogether? Well, it's hard not to think that one must be right and the other wrong, that either sets exist or they don't, that set theory is a body of truths or it isn't, that either the considerations cited by Cantor, Dedekind, Zermelo, and the determinacy theorists are confirming evidence or they aren't. But perhaps this tempting position is incorrect. Perhaps our strong conviction otherwise rests on what Mark Wilson calls, in his typically colorful style, tropospheric complacency. That is, we tend to think that our concepts, in this case true, exist, evidence, believe, know, mark fully determinate features or attributes, that there is a determinate fact to the matter as to where they apply and where they don't, that this is so even on questions that we haven't yet been able to settle one way or the other. Wilson's massive case against this picture, a book called Wandering Significance, rests largely on a wealth of fascinating and down-to-earth examples. To get a feel for how these examples go, let's look at two. Okay, so first, consider ice. We all know what ice is. It's frozen water. But Wilson takes us in for a closer look. He says, water, in fact, represents a notoriously eccentric substance capable of forming into a wide range of peculiar structures, close quote. He goes on to quote a recent textbook on the subject, which describes ice cousins, quote, the calthrate hydrates. Like ice polymorphs, this is the textbook talking, like ice polymorphs, they are crystalline solids formed by water molecules, but hydrogen bonded in such a way that the polyhedral cavities of different sizes are created that are capable of accommodating certain kinds of guest molecules, close quote. So Wilson remarks, quote, the author doesn't regard calthrate structure as true ice, but is it clear that our everyday conception of ice requires, as opposed to accepts, this distinction? I, for one, have never thought about such matters at all, close quote. It gets worse. There are, in fact, a dozen ways that water can form into a solid. In one case, if one cools water quickly enough, the result lacks crystalline structure and more closely resembles ordinary glass. Wilson asks, should this glass-like stuff qualify as a novel form of ice or not? Our chemist will presumably say no, because the stuff is not crystalline, but many of us would perhaps put a higher premium on its apparent solidity, close quote. Now, in fact, I looked around and some other chemists do happily call this an amorphous type of ice, and so on. So is there a right and wrong answer here? Our everyday use of the word ice clearly correlates with an objective feature of the world, the substance chemists call ice I sub H, or hexagonal crystalline ice. So ice clearly doesn't apply to liquid water or to sand or to window glass. But does it apply to amorphous ice? Is amorphous ice really ice? Wilson's thought is that nothing in our ordinary use or understanding of the term ice, indeed nothing in the underlying chemical facts that we subsequently discover about the many ways that water can form into a solid, in short, nothing in our heads, in our language, or in the world will force either answer to this question. And notice that this isn't a version of the well-known Kripke-Stinian challenge, what makes 1002 rather than 1004 the right continuation of +2 after 1000. We have here not the hyperbolic doubt of a radical skeptic, but the real case where, as Wilson puts it, the underlying directivity seemed genuinely unfixed. Close quote. A second example is more fanciful, but still quite compelling for all that. Imagine the inhabitants of an isolated island. Imagine they've never seen an airplane until one passes overhead and crashes in their midst. They might quite naturally regard it as a bird. Regard themselves as having learned unexpectedly that the world contains a type of bird very different from the ordinary birds that they're familiar with, a great silver bird made of metal. Now imagine the story again, except that this time the plane crashes undetected and the islanders discover it in the jungle with the stranded crew taking shelter in the fuselage. This time the islanders might reasonably regard it as a house, might well regard themselves as having discovered a new and unusual type of house. Is there any temptation here to think that one group is wrong and the other right? It seems clear that nothing in their pre-airplane concepts of bird and house, or the corresponding worldly resemblances, is enough to determine this, that either option is open to them as a consistent and defensible extension of their earlier concepts, that their choice is determined by sheer historical contingency. But notice, and here's Wilson talking again, neither set of alternative islanders has any psychological reason to suspect that they have not followed the pre-established conceptual contents of their words, bird and house, close quote. So here we see the psychological force of tropospheric complacency in its purest form. Now, could it be that a similar brand of complacency is at work in the case of the second philosopher faced with pure mathematics? Does the history and current practice of pure mathematics qualify it as just another item in the list with physics, chemistry, biology, sociology, geology, and so on? Do honorifics like true exists, evidence, confirm, indisputably at home in the other subjects, belong in pure mathematics as well? Pure mathematics arose out of our empirical study of the world. It remains an intensely important tool for that study, even in parts that weren't expressly developed for that purpose. It continues to be inspired by the descriptive and inferential needs of the natural and social sciences. If all this is taken to establish it as a body of truths, we've seen how the thin realist explicates the ground of that truth and how mathematical evidence manages to track it. But we've also seen how the arealist gives a plausible account of pure mathematics as a deep and vital undertaking that happens not to aim at producing truths. What I want to suggest now, or at least at last to claim, is that our central questions: is mathematics of a piece with physics, astronomy, psychology, and the rest? Is it a body of truths? Do its methods confirm its claims? That these questions have no more determinate answers than, is amorphous ice really ice? Once we understand the various ways in which water can solidify, how these processes are affected by temperature, pressure, and other factors, how the various structures generated are similar and how they're different, there's nothing more to know. We can reflect these facts in either way of speaking, or to put it the other way around, neither way of speaking comes in conflict with the facts. Some version of Wilson's tropospheric complacency, our tendency to overestimate the determinacy of our concepts, might well leave us convinced of the exclusive correctness of one or the other. It must be ice because it's solid. It can't be ice because it's not crystalline. But we've seen that this psychological confidence is often baseless and also largely harmless. Likewise, once we understand how pure mathematics developed, how it differs from empirical science, once we understand the many ways in which it remains intertwined with those sciences, how its methods work and what are they designed to track, once we understand all these things, what else do we need to know? Or better, what else is there to know? Just as robins are birds and bungalows are houses, physics and botany are sciences, but this isn't enough to settle the status of downed airplanes and pure mathematics. Just as amorphous ice can be classified as ice or as ice-like, mathematics can be classified as science or as science-like, and nothing in the world makes one way of speaking right and the other wrong. If this is right, then we, more self-aware than the islanders, should recognize that there's no substantive fact to which our decision between thin realism and arealism must answer. The application of true and exists to the case of pure mathematics isn't forced upon us, as it would be if thin realism were right and arealism wrong, nor is it forbidden, as it would be if arealism were right and thin realism wrong. Rather, the two idioms are equally well supported by precisely the same objective reality, those facts of mathematical depth. These facts are what matter, what makes pure mathematics the distinctive discipline that it is, and that discipline is equally well described as the thin realist does or as the arealist does. Once we see this, we can feel free to employ either mode of expression as we choose, and even to move back and forth between them at will. The proposal then comes to this. Thin realism and arealism are equally accurate second philosophical descriptions of the nature of pure mathematics. They are alternative ways of expressing the very same account of the objective facts that underlie mathematical practice. And here, at last, we have a form of objectivity in mathematics that doesn't depend on the existence of mathematical objects or the truth of mathematical statements, or even on the non-existence of mathematical objects or the rejection of mathematical claims. This form of objectivity is, as you might say, post-metaphysical. To return to the phenomenology with which we began, I suggest that this account of the objective underpinning of mathematics, the phenomena of mathematical fruitfulness, is closer to the actual constraint experienced by mathematicians than any sense of ontology or extra-mathematical epistemology. What presents it to them is the depth, the importance, the illumination provided by a given mathematical concept or theorem. A mathematician may blanch and stammer, unsure of himself, when confronted with questions of truth and existence. But on judgments of mathematical importance and depth, he brims with conviction. For this reason alone, a philosophical position that puts this notion center stage might be worthy of our attention. Thank you.
Okay, well, in that case, yes, sir.
Well, as a material scientist, I find your story about ice trivial. In this sense, if you want to talk about ice, you don't talk about it. You talk about the water molecule. It happens the water molecule can take many different forms depending upon how you make it, and you give it many different names. So the central feature about that particular material, whatever the form is, it's based on the water molecule. So the question I would ask you, what's analogous to the water molecule in abstract mathematics?
Well, I'm not sure I intended the analogy to go down into that level. My point was, the example was just supposed to demonstrate that we sometimes feel that we have a concept that will classify everything anywhere that comes up, ice, it's either ice or not. We think that, we have this confidence. But then when we start to look at the complexity of things, and of course you're right, water equals H2O is a little oversimplified too, right? Because water molecules do all kinds of funny things in order for water to be the way water is. It isn't a bunch of little H2O molecules bouncing around. They have to dissociate and all that. When we see all that, then maybe we begin to realize that our sort of simple concepts are not as determinate as we think they are. And I'm trying to use that to loosen up your intuition about thinking, well, set theory has to either be true or not. And say, well, you're comfortable with true from certain kinds of contexts where it's familiar, and maybe this conviction that it's got to either hold or not in this new case is no better than your conviction. Once you see all the details of how this new situation is like and unlike your old ones, maybe it doesn't look as determinate as it did before. That's the only reason for using the ice analogy. But you're right, water is a fascinating substance, even before you get to ice.
Okay. Do you want to?
I have a bunch of things to ask, but mainly I wanted to hear more about what you meant by depth exactly.
Oh, yeah. Wouldn't I like to have
That's very fundamental.
Yeah.
And I understand what you mean,
Mm-hmm.
but I'm just wondering if you could tell a little bit.
Yeah, I wish I had a better story, more story to tell. I recognize the fact that what I've said here has been pretty much metaphorical, right? And I'm not proud of that fact. I personally prefer not to do that if I can get away with it, but I don't know what to do at this point to say more about it. That's why, but again, I do want to keep away from the idea that we're not really satisfied until we have some kind of analysis of the concept of depth. Because I think that's a little bit of a wrong way to, that's a sort of impulse you might have. Well, tell me what it is. And I don't think that's going to work. I think what we have to do is look at the various cases. And that's why I did, kind of bore everybody with a bunch of examples there at the beginning, just so that you could sort of feel for, oh, well, yeah, of course, that is kind of convincing. And so you get the feel for the thing. But I don't have anything better than that. A student of mine is doing a little sort of field work on this and going over to the math department. And, field work is important in this kind of study. And talked to some mathematicians and sort of said, give me an example of a deep theorem. What do you think is, what does it makes it deep? if two people disagree about whether a thing is deep or not, what's going on there? And to find out stuff like, well, sometimes they'll say things like, well, one guy's missing something the other guy sees, or some other kinds of factors about fashion or money or ego or something are getting in the way, or something blah, blah. Oh no, that's consistent with this being an abstract thing. I mean, an objective feature that we can be right and wrong about. I mean, like, my belief now is that it's an objective thing we can be right and wrong about, but I don't have a defense of that.
Okay, right. So that was my next idea.
Yeah.
Was do you have an idea of truth? Like, what does it mean for a mathematical statement to be true or false? Is that just sort of, maybe I missed something, but is that sort of just a...
I wanted to get true and false out of, the goal was to get true and false out of the story, and exist and not exist out of the story,
Okay.
and focus on this other thing.
Right, okay.
And which isn't to say, well, maybe I should say it this way, which isn't to say that I have a real good story to tell you about depth, but at least I feel like I've focused this on what's a more organic feature of the mathematics than the things that than this other debate was about.
Okay, thank you.
Did you want to ask a second question? No. Oh no, I'm sorry. Did you want to ask a second question?
No, I'm okay.
Okay, so I have a list that's growing, but Zoltan, you're next.
Yeah.
To my surprise, you ended it with a kind of agnostic note, thin realists versus arealists. We cannot really see whether they can tell mathematicians how to understand the enterprise of mathematics. That sounded a little bit like writing zero for philosophers. They somehow cannot say. But I don't want to follow up on that. What I wanted to follow up on is you started with the problem of existence of mathematical objects, nature. That's a sort of non-issue. Mathematicians, even MacLean and others, have talked about it, but who talked a lot about it were the structuralists. They said it's the structure, not the entities. So I was curious, where do you stand on that in relationship to thin realism and arealism?
Okay. I've expressed I described thin realism here as a realism about objects, right, about the sets.
Yeah.
But just because I find that the most straightforward way, if you're talking about set theory, there's the little quantifier, there exists a set, blah, blah.
Sure.
Okay. But then you're right. There are people, mathematicians and philosophers, who want to say, no, Shapiro and all those guys, that it's not really about these objects, it's about this structure.
Yes.
Now, in fact, I don't really want to make any fuss about that metaphysical difference. If you want to put it in terms of structures, that's okay by me. And so there could be a thin realism about structures. It wouldn't be that much different from there'd be a little bit of a problem because set theory, you'd be going a little bit beyond what set theory says, because set theory seems to say there are sets, and you'd be saying, well, that's not quite true, there's this structure. But I'm sort of willing to give them that or something. But that kind of difference to me is not what I'm worrying about. If there's a contrast for thin realism, the contrast that's on the existence side of the thing, as opposed to arealism, it's what I call robust realism. And this is the kind of thing you find in Gödel. And I think in Shapiro, I think the realism that he has about structures is robust. The difference between the two is one quick way to come at it. Well, robust realism is the kind of realism that makes you think there must be a hard epistemological problem. That it's an abstract thing you've got to find out about. And it seems to me what you're doing there is you're starting from the metaphysics. What is mathematics about? It's about these objects, or it's about these structures, or something like that. And they're, maybe we even say it's sort of like an abstract thing, but it's just as objective as the physical world, and we say various stuff like that. And then we try to figure out what our epistemology and what our methods ought to be in order to find out about that thing. And that's where the big philosophical problem comes in, because you don't know how you, What the thin realist does, and what the second philosopher does, is by marching so relentlessly along the practical line of thought, she starts from the methods. The first thing she does, she figures out what the methods are, and she figures, well, that's what's sacrosanct. That's what has to be right. I mean, not each one is right. They criticize, but that way of doing things has to be right. And so let's find, the job is to find a metaphysics that matches that. And so you get then this thin realism. And so so the difference between structuralism or objects or anything like that doesn't matter so much. It's whether you think there has to be a non-trivial epistemology. A thin version of any of these things would think you don't, and the robust version thinks you do.
but then the structures, if I may follow up,
Mhm.
divide themselves into ontological structures and
Yeah.
epistemic structures. So
Yeah.
then how do you refine
Okay,
that?
let's see. Now, an ontological structuralist, that's like Shapiro, right?
Yeah, yeah.
Whatever it is, right? And that's really a form of robust realism.
Right.
Okay, now what's an epistemic structuralist?
That the only thing you can know is structures. You cannot go or relations about structures or properties of structures or things like that. You know,
But
so
that's
you-
still that's still a sort of realistic I mean, that's still a thing that exists objectively, independently of us and all that, and we need to somehow glom onto
yeah,
it.
there
right?
has to be a referent of
Yeah,
what you're supposed
yeah,
to know. Yes.
Yeah, I think that still counts as a version of robust realism. So for my purposes, this is very crude categories.
Yeah.
They would all fall under robust realism.
Thanks.
Sure, thank you.
Peter. I thought I saw your hand, sorry. Well, you,
Oh, wait.
I think, oh, was it yours? Okay, I saw a hand come in. This was following up on your question on how to measure mathematical depth.
Okay.
So I mean, it actually follows up on your statement as well. If you just view mathematics as a web of implications, right? I mean, an easy way to define depth is just you look at a node and you look at the number of sort of vertex edges emanating from that.
Oh, yeah, but
And I mean, sure, it's cheap because
Yeah.
definitions, everything
Yeah.
can just.
yeah.
But
I mean, that.
still, there's a well traversed.
I mean, look, the same number of logical things are going to come out of anything, aren't they? I mean, if you start counting or something. I mean, you got to be able to distinguish the interesting ones, right?
Yeah, I don't think it reflects mathematicians' opinion.
Yeah, yeah.
Because of the definitions you can make things which are completely unrelated via a very complicated proof turns out to be the same.
Yeah.
These are really the great things in mathematics.
That's deep. Right, that's deep.
It's only because you are able to define. I mean, you simply
Yeah.
write down something which is not contradictory, and the question is this equivalent to something else which you also wrote down, which is not contradictory? And the proof can be thousands and thousands of pages.
This is one of the things that people do cite as a symptom of depth, for what it's worth, is a case of that would be where you found, you had these axioms of large cardinals, which, I mean, all they do is they're a way of saying that the, V goes way, 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 way up. And on the other hand, you had these determinacy hypotheses that are about, infinite games on sets of reals. That came out of measure theory, completely different sort of thing. And it turns out that these are the same, they connect together. Well, gee, we must be onto something. So that's one common symptom of depth, for what it's worth.
So I actually had you next.
Yeah, so I was going, to comment. Actually, it's great that we got to this point. It seems to me that you put some sort of a partial ordering on fruitfulness, and you're hinting to this, to the existence of a total, ordering in some sense out there, or nearly, or at least, your definition of a set was a maximally effective tracker of fruitfulness.
That's
So
not
I
a
wrote down
definition,
as
it's-
you were,
It's a poem.
What I was going to say is that there are still areas of mathematics, say stability, where there is no such, measure of, fruitfulness. You can have very messy definitions that, so basically, and narratives that seem to be connected, but in no clear way. And there are, areas that not only are they messy now, but we are not in fact sure that that will ever be resolved. So that is, one issue. So having that as your mechanism for the advancement of knowledge, I have a, slight objection to that. That's one point. And then the second point is that some of us actually do mathematics not only by measuring this fruitfulness, but also by looking what is not there. So in a more, postmodern way, what is absent and why? It's actually the next question to ask. So that's a different mechanism than what you proposed.
I'm not sure I understand. Let's do the first one. The first suggestion was that there are areas of mathematics where
it's not so clear that there is this maximal fruitfulness measure.
Well, I think
that
you're
can be
taking that
imposed.
maximal a little too literally. As I say, this is all kind of metaphorical. But surely there are distinctions in stability theory between, you define the central notions have to be ones that are thought to be the important ones as opposed to ones that wouldn't be important.
The problem
No,
is that
everything's
there are-
important, nothing's
The problem
important.
is that, you know, there are several competing notions. They interact in some way, but none
Mm-hmm.
actually explains, you know, everything. So in other words, the picture is inherently very messy.
Mm-hmm.
And it doesn't look like it's going to be resolved. Maybe we are going to see in the next, you know, 20 years this beautiful, you know, resolution that will simply, you know, basically bring more evidence to your, you know, ordering of, you know, fruitfulness and, you know, mathematical depth. But we might also be pursuing various, you know, narratives that may interact in very complex ways that don't.
I don't see
have
why
this
I'm worrying
progression.
out, I don't know why I'm ruling out complexity. I mean, intermodal theory is very complex, and so is large cardinal theory. I don't see why I'm.
But it's not so much,
What
you
is
know,
it that's bothering me?
complexity,
I mean,
but rather
there are concepts that are the central concepts of stability theory. No, there's several that are the.
There are several, and
That's
in fact,
okay.
not one, you know, can take precedence over the
Well,
others.
why is that? I mean, you don't want to. You talk about groups, but you also talk about fields. So there isn't any reason to choose between those.
Not in the same sense, in the sense that people are looking to explain the same phenomena, and they have these various definitions that cannot be sorted out. You know, in some, you know, they cannot be ordered, you know, a certain way. So they, you know, each captures a little bit of the picture.
I'm missing why that is something I would want to somehow rule out.
It's not that you're ruling out from your presentation. It looks like you're, you know, expecting. So you put as the mechanism for the formation of knowledge, that of, you know, new knowledge that you put forth, was this, you know, investigation of, you know, fruitfulness. So in other words,
Yeah.
closer to Zermelo's claim.
Yeah.
And
And
that's
you
what
have a
I'm
case where
objecting
you've
to.
got several concepts, all of which are fruitful, none of which can replace the others.
They are not so fruitful, actually. That's the
They're not so
problem.
fruitful, then
They
what
do
are you
not-
bothering with them for?
Well, that's the problem. There is a phenomenon that's precisely the problem. It's a phenomenon that people are trying to capture, and you know, none of the, you know, definitions. So there, you know, it's you know, very broken picture. In other words,
If it continues to be broken and there's no mathematical fruitfulness, why do we continue to do this thing?
because it's related to a bunch of other, you know, areas. So people
Uh-huh,
are still hoping to elucidate. The
Well, there you
relationship.
are. They're still hoping to get
They
at
are
what the
hoping,
depth
but the problem is that, you know, it may stay messy. So there might not be a resolution, in which case, you know, your idea of a narrative may not play out in that
in the sense, well, so what happens to the field if that happens? 50 years from now, people have been beating their head. This is really bad. I hate to do this because I don't know what we're talking about. And I always feel much better if I actually understand the examples. So I'm not liking this at all.
We actually have a geometer in the audience. Chris, would you be willing to comment on, you know, stability and the mess?
I don't know what you're talking about. Mess and stability.
So you have different notions of, you know, stability and, you know, different ways in which people are getting at that, you know, so basically, you know, complex geometry.
So your notion of stability isn't the logician's notion, it's the geometric.
Yeah, it's basically, you know, you know, there is within a certain sub-area of geometry, people are
But
have this
you're not
competing
using it
notion.
as Shayla uses the word.
No.
Ah,
No, it's not stability in the sense
Okay.
of a model theory. It's a different notion of stability
Yeah,
where
okay.
we really do not know.
The
This
public
state's very
notion.
important.
Okay, the
and,
public
We really do not know. What is it we really do not know?
the public notion of stability is I think. what
Excuse
you
me?
used. The more public notion. Some systems are stable, some aren't.
Oh.
Sorry, I was
no,
misunderstanding it.
Okay, yeah, I thought we had a technical, yeah.
No, it's a technical notion within, you know,
Well,
geometry.
you told
So
us it's several
stability-
different ones, and we
that,
don't
you
know
know,
which one is the best one. It's
That's
like,
exactly for, you know,
right?
say again?
Is this like, let me ask you this. That's right. Let me ask you a question. So at a certain point, we were trying to understand the notion of computability or algorithm or whatever, right? And there were several different things that were proposed, right? Lo and behold, they all turned out to be equivalent, which was one of those cases where we thought, oh, we must be onto something, right? Another way that that can happen. But in their case, that hasn't happened. They're all still separate. Is that right?
So that's precisely the thing. We may
Yeah.
very well uncover areas where this messiness of the subject, of, you know, the narratives may persist.
Okay, then you're going to have to tell me why you think this is a fruitful area to, why is this fruitful? Well, but does it? Does it? Yeah.
You know, in
One of
some-
these, you use difference of these. Well, I just don't know why I have to. If each of these notions is useful in some way, then each of them is onto something, and that's fine. If none of them are onto anything, why do we bother? Am I insisting that they all turn out to be the same? No. So I just don't. Do you understand why this is a challenge?
Yeah, I think the point she was trying to get at is that you seem to always identify that there's going to be an umbrella term. or something-
Yeah, and I don't.
something
If I said that, I didn't mean.
I mean, and
I
so,
don't
like,
mean
the
that.
concept of
Yeah.
set somehow captured a lot of other ideas.
Oh, I'm just talking about set theory, though.
Yeah, yeah, yeah.
You know,
But
so
I think
naturally,
what
I'm
she- I
talking
think
about
what
the idea of
she's
set.
talking about is right now, it's the same thing that Riemann struggles with, to somehow come up with a rigorous notion of space.
Mm-hmm.
And there we did
Yeah.
develop one. We had a manifold, right?
Yeah.
It was a good definition. But
Right.
we're still trying to find a
Yeah.
definition
Yeah.
that summarizes all the other.
Right,
You know-
and that seems perfect. You know, there's nothing wrong with that story. The question I think is being raised is, what if that never happens?
Exactly.
Yeah, and I don't know.
That's
Depends.
also true in mathematical physics. We had a beautiful colloquium a week or two ago, precisely in this very complicated relationship between applications of physics to mathematics, but more importantly mathematical physics. And the situation there is kind of pretty much a broken relationship that doesn't seem to be resolvable. So what I'm saying is simply an objection to what you've identified as the mechanisms for the creation of knowledge. So this mechanism of depth and somehow the narrative, and also my second point that sometimes one can simply look at absence, the absence of a concept, the absence of a certain relationship.
I think I'm just going to have to pass on this because I'm not sure I quite understand what you're asking.
We can continue doing
Yeah.
the reception.
The
Okay.
gentleman next to the slide projector, please.
Okay, I'm like the second philosopher that you're mentioning. I am in some of the department, material science and engineering. I do experiments and I try to evolve my own philosophy of mathematics.
Okay.
Well, to start with, this is more sort of a comment, and I would like you to give your comments on this one.
Mm-hmm.
So, what I find is there's a mathematical structure in every physical object that we see. Like, say, a protein or something. You can describe a protein as something which minimizes some statistical potential. A set of. Okay, please excuse my mathematical sense here, but there is a function called a statistical potential, and proteins are sets of things that. And you're performing a mathematical operation on this thing called statistical potential, and so whichever minimizes the statistical potential, you can describe everything mathematically. That's what I'm getting.
Mm-hmm.
Similarly, take for example transistor. Transistor is completely engineering oriented, but you can trace back its roots to say Hilbert spaces or whatever, quantum mechanics.
Okay.
So what we have thought was abstract, say 100 years ago or 105 years, 150 years ago, is slowly getting to what is the real world. Like-
Do I really think a protein is a... Okay, so here's some mathematical description of a protein.
It's
Do I think that the protein is exactly that?
Yeah. So
I mean, or as opposed to usefully described as being similar to that in some ways?
No, it can be usefully described in some other way, but it can be described also
Yeah,
in that way.
but that doesn't mean it necessarily has exactly that structure.
Yeah, so let me complete my point.
Okay, sorry.
All right. So 150 years ago, we just thought we were in this normal three-dimensional space.
Mm-hmm.
And then this guy called Albert Einstein came and said, well, there is a 4D space-time curvature. So whatever you think of, so this spaces other than Euclidean spaces also have come into reality. So the real world is something which is like evolving as time progresses.
Real world didn't evolve. We just understand it better.
What we perceive as reality.
What we know about the
What
world.
we know about the
has-
world. So perhaps there's at the risk of running into a conclusion. So my point is, we are like, I am actually agreeing to whatever you said. We are like the Icelanders that you mentioned, who need to be more aware about everything else so as to keep everything in perspective and look at the aeroplane as an aeroplane rather than rather
I
than.
tried to make it a house or a bird.
Yeah. So,
Right.
so at the risk of extrapolating it further, nature is mathematical. What I feel is the language of nature is mathematics. And if God or somebody exists, they speak in mathematics and not in whatever Sanskrit or Hebrew or whatever. And as physicists, we are trying to understand the language of nature.
Okay.
So, well, your comments.
Okay. I sort of like the thing you said about we ought to be more self-aware than the islanders and not try to make everything into a house or a bird. Because I think that's what happens a lot of times when people think about mathematics. They say, well, you know, it's like science, or it's like fiction, or it's like a game, or something like that. And it always, you know, and sometimes those can be illuminating in some way, but usually they're in some ways more distorting than they are illuminating. And it's always seemed to me, let's just stop with the metaphors here. Let's just try to describe mathematics as it is. You know, granted, mathematics is a hard thing to understand, and that's why we keep wanting to make it like something else. But I think it's just better to come at it straight. And that's part of what I'm doing here. Yeah.
Was abstract sometime back, it's no longer abstract.
Well, that, you know, what you were saying, it's lovely. What you said is what Galileo, you know, said, that the book of nature is written in the language of mathematics. In fact, he thought it was written in the language of geometry, right? And Newton thought that, and Euler thought that, and Fourier thought that. But, well, there's sort of a interesting, actually, I think there's a very interesting history to that view, okay? Because at that time, with all those guys, there was an idea that really math and science were the same thing. Right, as we were studying the world, we were just finding out what God had said when he uttered his mathematical claims, right? And in fact, there was a portion to this methodology that involved, well, so there were two things. One was that there is a literal, you know, mathematics is the structure of the world, right? And that what we should do is just describe the phenomena and not try to get any, you know, mechanistic kind of explanation of what's going on. So for example, Newton says, I'm just going to tell you what the laws of gravitation are, and I'm not going to tell you what the mechanism, I do not feign hypotheses. And this was a brilliant strategy, and it carried forward, and Euler did the same thing, and Fourier says the same thing when he's doing heat. I'm not going to talk about caloric. And the things that were on the other side, though, at those times, for Fourier was caloric theory, which was just a mess. For Newton, the thing that was on the other side was Descartes' theory of vortices in the plenum or whatever, you know, which is also a big mess. And the idea everything had to be contact forces and all this stuff. So these guys that said, no, let's just give a mathematical description of the sort of phenomena and don't expect science to give us these underlying mechanistic stories, were really in the right, absolutely. But then you get up to it sort of develops over the 19th century, because the thing that's on the other side turns out to be actual atomic theory. You get Dalton and you get atoms coming into chemistry and all that stuff. And the people in the Galileo-Newton line of thought are the energeticists who say, let's just do thermodynamics, right? So, and so we don't want to look at any mechanisms. We're just describing what happens. And it's a perfect theory. Water, you know, the spilt milk never does get back into the glass. You know, they're absolutely right about this, right? But that other theory on the other side just kept getting better and better and better, right? It got swept through chemistry and did all this good work, and then it went into kinetic theory and did all this good work. And eventually, at the beginning of the 20th century, experiments were done that convinced people that atoms were real. Now, what happens then? Poincaré even issued this sort of, you know, plaintive cry. If that turns out to be right, then these differential equations that we've had for all of these phenomena will no longer be literally true. They'll just be smoothed out versions of, you know, a very more complex thing. And in fact, the water might go back into, you know, okay? So the perfect phenomenological theory gets overturned by the mechanistic thing. So once that happens, this picture that was so nice from Newton and Galileo on really isn't available anymore, because we now think that those nice differential equations are just approximations, or something like that. And if you look at the rest of science, you go through the various places where you might find the math describing things literally. Usually you don't. I mean, maybe in the very beginning of statistical mechanics, when you're just counting, how many molecules are at which side of the thing, maybe. But very soon you're doing calculus on that, which is wrong because they're finite, So it seems to me that what happened was that the mathematics really has peeled itself away from the world, and we have these very complicated mathematical structures, and we don't, we know some things about how they relate to the phenomena that we're trying to describe. There are very many things that we can only say about the phenomena by using the mathematics, but we don't think that God is speaking in those differential equations in the way that we once did, and that makes it a somewhat different picture. That's sort of a long story, but it's lovely, though, to think that way, and I think you go ahead and think that way. As scientists, it's fine. Sorry, was that too long?
No, that's not all. I'm next, so. Before we forget about the fruitfulness thing, I want to just go back to it. So, I wanted to, mathematical fruitfulness is a key notion for you.
Yeah.
And then when you spelled it out, most of the time you talked about depth.
I like the word depth better.
But not always. And once in a while you hinted at something else, which I wonder if, in sort of as your fellow naturalist, if maybe could be expanded. So you sort of hinted at something about how like a research program is fruitful. And so what I wanted to just do is say we could maybe develop this. So there's a kind of standard way that people talk about grounding objectivity in the natural sciences in a naturalist way, and kind of drawing on Lakatos or something, and sort of looking to the fruitfulness of a research program, a non-degenerative, fruitful research program that's extending itself, explaining new things, going to new territory. So, I'll put it bluntly. Why mess around with trying to really give a kind of account of depth, since as you said before, it's hard to get beyond metaphor there.
Yeah.
Why not actually go for something like fruitfulness of the research program? And literally how productive is this, and grounded in the community of inquirers, not in something about the world which you're sort of which you're sort of uncomfortable doing anyway.
Well, I want to ground it in something. I want it to be objective.
Well, that would make it objective.
And no, that makes it intersubjective.
Well, we're naturalists.
Ain't good enough. No, that's not naturalism, man. This is objective. That's not just an intersubjective blah blah blah. That's a chair. Right? So I'm aiming for that level of objectivity here. That might not be right, but my first try anyway is to think that whether we had discovered groups or not, those logical well, one thing I might say is that I do think logic is sort of logical connections for the most part are kind of robustly true. So that logical mesh thing, that's real. Okay, and then so somewhere in that logical mesh thing, if you put the concept of group in there, something happens, and whether we thought of it or not, it would have been a mathematically fruitful thing I'm using fruitful and depth and important and all those as interchangeably. So yeah, it would have been a mathematically deep concept. Now, I don't know really what happens when you translate over to talking about research programs. Are you saying group theory is what did you call it? A fruitful research program. You could say that, which would be fine. But I think that's an objective fact about how group works in a mathematical way, how the concept of group works in a mathematical way.
So fearing you would not want to go that way, let me just try one thing on you. Here's a way of articulating depth that's maybe non-arbitrary. You could try to use the machinery that was developed for the unification accounts of explanation. So it's something like how many propositions you can capture, but then constrained by sort of criteria that let that not be arbitrary, where you're just sort of adding disjuncts. So it's sort of like, how much you can do with how little, and you can try to formalize that notion.
Okay, well, here's something maybe to say, is that I tend to think of it, this is just how I tend to come at it, is to do what I was suggesting that my student is doing, which is go over to the math department and ask some people what they think. And if you're going to say something general about what mathematical depth is, to try to glean it that way. So maybe then at the end of days, when you know all that, you can do some kind of formal thing where you do that kind of thing. But I think the other thing comes first. So let me give you an example of this. Some of you may know Harvey Friedman. He has done a lot of work trying to show that certain set theoretic axioms are required to do what he calls core mathematics. And he thinks this is important for for the long-term welfare of set theory, that it get integrated in with core mathematics. Now, I used to think, it used to puzzle me. I'd think, why are we worried about that? Because obviously this set theory is a fruitful research program. It's going to town, new theorems, deep concepts. It looks like, all this stuff is happening there, doing all these things, right? Why this business about tying it into core mathematics? I mean, I can see that as a sociological matter or something, because, mathematicians scoff and you want them to stop, or something like that. But is there any real reason for that? And I couldn't, apart from sociology. And it seemed to me not. But then I started thinking about, that was before I started thinking about depth. And when I started thinking about depth, I realized that I think that what you find when you do your field work is that a lot of mathematicians will say, well, what's really deep is a theorem that ties together this part of math and that part of math. Things that you didn't expect to all be related to each other come together in this one thing. Who would have thought, right? And if that's right, if somehow that's a requirement on being deep, then you start to see why it would be important to get higher set theory hooked in, right? Because it can't really be deep if all it's doing is its own stuff. Now, I don't really know if that's right or anything, but I start to feel like this is the kind, anyway, that's the kind of way I come at the question, is to try to sort it out in terms of the particulars. And then maybe there'll be a general theory and maybe not. But as I said, the general theory isn't going to be what's given the justificatory force. It's going to be whatever it is that's happening at the ground level.
David.
Yeah, I was actually wondering in terms of the perspectives on what to introduce as an axiom.
Yeah.
You had mentioned the continuum hypothesis. I'm just wondering whether these points of view shed any light on the question of whether to make it or its negation or neither an axiom.
Well, I think nobody wants to make either of them an axiom, and why exactly is hard to say. They just don't seem, they're too special or something. I don't think anybody's done a good study of why one thing is an axiom candidate and another thing isn't, but somehow CH isn't. But the current state of play, of course, is that the hope was large cardinals might be able to do something, because they do tell you stuff about projective sets that the classical guys wanted to know, and they give answers to that. So maybe that. But back in the 60s, it was shown that's not going to do it. And so then maybe determinacy, but then determinacy follows from large cardinals, which is a great thing, but it also means it's not going to settle the thing. So I guess the most well-known thing that's happened recently is some work of Hugh Wooden on this. But do you know about this? Or, yeah. But who knows what that's going to turn out to be? For one thing, it depends. We've always known it depended on the truth of this thing called the omega conjecture. But it turns out, this is facts known only to Hugh, right? Because he understands all these things. There's another thing, the AD conjecture, right? That you need two. And so now it's not just the omega conjecture, it's something called the strong omega conjecture, which is the old omega conjecture plus this new thing. So there's a sort of big chunk that has to sort of be fit into place if that's ever going to work out. And he's got an alternative thing that he's now thinking about, this ultimate L.
But in terms of like these, let's say these 2 points of view.
But you see, as far as these 2 points of view, they agree completely on any of that. It's completely irrelevant. That's what makes them seem like they're just floating free of anything that matters. That's the point. Yeah, that has no significance for that whatsoever. That's what makes me think it's not a good question. And this happens actually, I think, in a lot of philosophical problems, some philosophical problems where somebody wants, I want an answer to this question, And you say, well, look, here's the situation. Here are all the details of the actual thing you're talking about. Now, I'm not sure which of those is the right thing to say, and I tend to then think so much the worse for the question, but maybe you can come up with some reason that you still want to say one or the other, but to my mind, you've got all the facts here, and if it floats free of those, right. Sorry, I didn't understand what you were asking at first.
When you said it's not a good question, you meant the H there. Continuous hypothesis is not a good.
No. I meant the question of do they exist or not.
Ah, okay.
It turns out to,
Oh,
yeah.
that's
No. This is a good question. I sure would like to know the answer.
First, a historical point. Otto Neugebauer was convinced that the Greeks were atomists at heart. And
Who's
therefore-
convinced?
Neugebauer?
No.
You know that. Usually considered to be the greatest scholar of ancient mathematics of all time. Sorry. He was convinced that he discovered Babylonian mathematics. The difference between the 1911 Britannica and the more recent Britannica on the history of mathematics is all due to one person.
I see.
He was convinced that the Greeks were atomists at heart, and that they invented things like axiomatic methods precisely because they didn't believe they were true.
Who was true?
Those axioms.
They thought the axioms were not true.
They were an approximation,
Really?
akin to writing down differential equations for something
Really?
even worse than atoms would be populate. Demographers are filled
Oh,
with
sure.
differential
Oh, sure.
equations, and they're
Yeah.
talking about people.
Of course,
for God's
of course.
sakes.
No, it happens all over the place.
Right.
It's
But
just,
it
I was
is
just
ancient.
looking at the places where we
So-
thought that
so
it was not.
Neugebauer wanted to argue that the whole reason for Euclid to write down his hypotheses, or axioms, whatever you want to call them, was because they didn't believe them. They wanted to keep track of them for that reason. So notice other things like all sorts of betweenness axioms aren't there, because they would remain true even in the presence of space atoms. So space.
It's like Goldman Sachs marketing.
Well, except he didn't think that they were. He thought it was. Everybody knew that at the time.
Since
You
they
wouldn't
were,
buy it.
But let me. By the way, a more recent historic point is that 20-odd years ago, when I first started arguing with Harvey Friedman, he didn't believe that at all about the relationship, about the need for
No.
logic.
no,
And-
he's
and-
changed his tune.
Yes, he certainly
Yes.
has.
Yeah,
He said-
yeah.
there was a time when he credited that. Never mind.
Yeah.
Another point I'd like to make, or just off, is this tendency to think that mathematics was something to do with physics. Yes, it was. It was also something to do with gambling and other ways of making money. And that totally changes the view of what you would take as foundations, which led, for instance, to the interesting possibility that stat departments would want foundations in which the axiom of measurability was true. and
Well, you
other
can
people
have that.
wouldn't.
You can have that if you want. You
Well,
just-
you know that I'm preaching for a more flexible view towards foundations.
Yeah, but see, okay, so my inflexible view is
That.
if you really want to just use measurable sets, you just work inside L(r) where all the sets are measurable and you're fine.
Oh, any geometry can be modeled in any other geometry too, but that doesn't change the fact that we very much change our minds about the absolute nature of geometry. Yes, we know perfectly well that any good foundations could be modeled in any other foundations. Why not? So
Well, I'm
what?
not so
Here's
sure.
the
I'm not
question.
so sure that set theory can be modeled well in category theory.
Of course it can.
Not higher set theory.
Yeah,
do,
sure.
do we know this?
I'm not saying it's fruitful.
I've asked
I'm saying-
category theorists
well,
about large cardinal theory and stuff. Most of the set theories that you get in category theory are fairly weak.
It's trivial to do so, but it wouldn't be interesting.
It would not, yeah, because you'd be putting it in a place where it isn't a natural place.
Right, that was the point I was trying to reach. That the fact that an awful lot of it comes down to whether things are interesting. I mean, I found myself saying that as a freshman to a professor of philosophy who was sitting next to me at lunch. I think this was the second week at school, and he said, "What do you think about?" And he mentioned what were then the 3 points of view: intuitionism, formalism, and logicism. And I said, "Oh, I think it's just a matter of which you consider interesting." Not knowing at all what he was talking about.
Right.
And I then proceeded to sting that. I said, I'm sure that you could use any of them to talk about the other thing, but it wouldn't sound interesting when you made that change. Yes, I mean, that is indeed the point.
yeah,
That
yeah.
Of course you could do set theory in category theory.
Well,
it wouldn't be interesting when you did it.
well,
You wouldn't, first of all,
well,
be gaining anything.
Well,
Set theory in the sense that you mean, the large cardinal
yeah,
stuff.
yeah.
Of course you could, but so what?
Well, the category theorists I've talked to are not as...
Well, then they haven't thought about it long.
All right, they haven't thought about it long.
Peter's book, no doubt.
Right. Well, let me...
No, this is all. This,
A lot of category theorists say that doesn't matter. That higher set theory is degenerate stuff anyway, so who cares? So category theoretic foundations are fine. But let me just say this. I'm completely committed to the idea that there are lots of areas of mathematics that are better expressed in category theoretic terms than in set theoretic terms. That doesn't bother me at all. There are lots of areas of mathematics that you would want to do in different terms. I mean, I'm not, you don't want to say an algebraist has to talk as if he's a set theorist all the time, or a topologist, or a geometer, or anything like that. What set theory is trying to do is just provide a certain kind of, ultimate foundation if you get into trouble. When you think about the history of the thing, here's the way I understand the history of the thing. So you had the mathematics peeling off of the science in the way that we talked about before. Or gambling, or whatever it peeled off of. Okay. And then you had at the same, really during the same time, the 19th century, you had the rise of the idea of doing, studying kinds of mathematics that didn't have any obvious foundation or application, and not really caring, and about, and Euclidean geometry becoming not the geometry of space, but one of many abstract spaces and all that stuff. And that whole line of development ended us up with this picture of pure mathematics. And the ways of doing the pure mathematics could not be tied to the physics or the gambling or whatever it was in the ways that it was before, right? When Euler would do some kind of an argument, he could use some physical intuition in the middle of it if he wanted to, just in the way that Euclid used some stuff from the diagram. It was perfectly fine because it was all the same stuff. But when you get to this really pure mathematics that's separate and autonomous and all that, you now have to ask yourself, well, what's right and what's wrong, and how can we decide what to do? And so you had the idea that, well, if you set up an axiom system, that's pretty good. But people knew that you could think you were describing a structure and actually be messing up, So you had to have a way of deciding, of adjudicating between the kinds of structures that were legitimate ones, coherent or whatever you wanted to say, and the ones that weren't. And that was one of the roles that set theory developed to fill, right? And so it did. And for the 20th century, everything is happy and copacetic, right? And so now people are happy to say, oh, well, you just figure out what axioms you want to use and prove theorems from them, and they just sort of shrug off the worry of, well, are those axioms inconsistent or not, but that's the real problem that inspired the move to set theory set theoretic foundations in the first place. So it's easy to be complacent now because set theory has done such a good job.
It was an important part of mathematics. It really was.
What wasn't really important?
The set theory. Mathematicians didn't pay attention to it. By and large, they were talking about things in which set theoretic problems did not arise. and they scoff at it, and with reasonably good reason.
Okay, all right.
I think we have like 2 minutes, so time for one last question.
I really enjoyed your presentation, and
no, thank you.
Such a complex array of issues in philosophy of mathematics and science. And trying to link philosophy to science is a very tricky, obviously very tricky project. So, but there was one thing that I had a question about, which you said, that real world does not evolve. And
you mean in response to you? Yes. I meant that the real world didn't go from being three-dimensional to being four-dimensional. We just found out that it was four-dimensional. Yeah.
But we don't know it's four-dimensional.
It can be a bit.
It could be 11th dimensional for all we know.
Oh, yes, okay, fine. But the point was supposed to be, it was just a simple point. The way he expressed it in a way that I thought, okay. Is that all that we were worried about? Yeah.
There was, it does evolve, globalization, consequences of action, effect, and cause, they're all evolutionary.
Right. All I wanted to say was, there is room to say that our theory, that it isn't that the world changed, that our theory of it changed.
Yes.
And in these kind of cases, I would want to say that. Yeah. Okay.
So I think we should thank Professor Maddy for a very stimulating.
Thank you.